Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 7.1 by looking at a couple more examples of determining the eigenvalues and corresponding eigenvectors of different matrices. In the previous two videos, we've seen a couple examples of doing this. Our first one, we saw that we had all real eigenvalues and real eigenvectors, and in the previous video, we saw that we had a mixture of real eigenvalues and complex eigenvalues, and therefore a mixture of real eigenvectors and complex eigenvectors. So far, though, we've had this sort of unique situation where the number of distinct eigenvalues has always matched the size of our matrix. And as we know, because of the fact that the characteristic polynomial is of the same degree as the size of the matrix, we can never have more distinct eigenvalues than we do the size of the matrix. However, in the two examples we're going to be looking at today, we're going to see that we're going to actually have fewer eigenvalues, at least distinct eigenvalues, compared to the actual size of our matrix. And we'll talk about this situation a little bit more in depth, and then we'll be ready to move into section 7.2. So let's go ahead and take a look at this example here. So we've got this square matrix 3, 2, 0, 0, 1, 2, 3, 3, 4. We want to find the eigenvalues and corresponding eigenvectors. So as always, let's go ahead and start with the eigenvalues. So we want to take the determinant of a minus lambda I, so that's going to be 3 minus lambda, 2, 0, 0, 1 minus lambda, 2, and then 3, 3, 4 minus lambda, and we want to set that determinant equal to 0. In this case, it's probably easiest to sort of expand along column 1 or row 1, whatever you sort of prefer. I'll go ahead and use row 1, so we have 3 minus lambda, and then times the resulting determinant from 1 minus lambda, 2, 3, 4 minus lambda. And then this guy, of course, is in the 1, 2 position, so it's actually going to have a negative coefficient, so negative 2, and then the determinant resulting after we sort of remove that. So it looks like we should have 0, 2, 3, 4 minus lambda. And that's got to be equal to 0. So let's go ahead and get those then. This is going to be 3 minus lambda, and then we'll have some parentheses. We've got 1 minus lambda and 4 minus lambda, and then minus 2 times 3. And that's good there. And then we have minus 2 times parentheses. Well, the diagonal here is easy. That's going to be 0, and then we're just going to get minus 6. So that'll be equal to 0 then. So we can go ahead and start simplifying. Well, I guess actually first we got to expand here. We're going to get lambda squared minus 5 lambda plus 4 minus 6. And then this is going to be plus 12 at the end there. And then it looks like we get 3 minus lambda. And then in here we've got lambda squared minus 5 lambda minus 2. And then plus 12 equals 0. We'll have to go ahead and directly FOIL this out, though. So 3 lambda squared minus 15 lambda minus 6. And then minus lambda cubed plus 5 lambda squared plus 2 lambda plus 12 equals 0. All right. Our leading thing is actually a negative lambda cubed. So let's get that in the front. Negative lambda cubed. Then looks like we get plus 8 lambda squared. Then we've got minus 13 lambda, and then looks like we've got a plus 6, and that should equal 0. Now, probably easiest if our leading coefficient is actually a positive 1, so let's multiply everything by negative 1 there, and get lambda cubed minus 8 lambda squared plus 13 lambda minus 6 is equal to 0. So we've got our characteristic polynomials there. Now we just need to solve it. Now, if you haven't been solving a lot of cubic polynomials in your spare time, right, the trick for doing this, of course, is that we'd like to reduce it in order down to something that's a little bit more manageable. So we probably want to try to use like a rational roots to make some guesses about what might be a sort of potential root here. So keep in mind that any rational root would need to be a divisor of 6. So we got things like 1, 2, 3, and 6. If you think about 1, if we use like lambda equals 1, we'd get 1 minus 8, so that would be minus 7 plus 13, which would be 6. Minus 6 would be 0. So lambda equaling 1 should be a root, so lambda minus 1 should be a factor. So let's go ahead and do a little bit of long division. So we're going to do lambda minus 1 into that lambda cubed minus 8 lambda squared plus 13 lambda minus 6, since we know that that's going to come out evenly. we're going to get lambda cubed minus lambda squared. So that looks like we're going to get negative 7 lambda squared plus 13 lambda. Then looks like we get minus 7 lambda, so minus 7 lambda squared plus 7 lambda. And then looks like we get 6 lambda, bring down the minus 6, and then we should get plus 6 there. So once we do that, we can go ahead and sort of just swing this over to here. To finish this up, we know that this guy actually factors as lambda minus 1 and then times lambda squared minus 7 lambda plus 6 equaling 0. Now we need to go ahead and see if we can break this down further. But of course this is quadratic, so you could use quadratic formula or just see if you can spot a factorization. There should be a pretty straightforward one. This should break down as lambda minus 1, lambda minus 6. And it looks like we're going to get two eigenvalues, lambda equals 1 and lambda equals 6. So you will notice here that we got fewer eigenvalues than the size here, right? We were looking at a degree 3 characteristic polynomial because we had a 3 by 3 square matrix, but we only found two distinct eigenvalues. Now, later on in our discussion in 7.2, which will be in our next video, we'll sort of talk about this and we will say that this right here, this lambda equals 1, this is an eigenvalue that has multiplicity 2 because it actually shows up as a root twice. So we'll just make a sort of comment here. This is m equals 2, whereas this guy only shows up m equals 1. And that m there is just standing for multiplicity. How many times does that show up as a root or solution of our characteristic polynomial? Okay, now we'll go ahead and do our eigenvectors the same way. So let's start with the lambda equals 1. So we'll give ourselves a new page here. We'll go ahead. Eigenvectors for lambda equals 1. All right, so for the eigenvectors for lambda equals 1, we've got to go ahead, subtract a minus 1 times in, and then augment with the 0 vector. So we should get 2, 2, 0, and then 0, 0, 2, and then 3, 3, 3, and we'll augment that with 0, 0, 0. All right, should be pretty easy to go ahead and solve that. We can begin by using R3 and replacing with R3 minus 3 halves R1. And then we should get 2, 2, 0, 0, 0, 0, 2, 0. And then looks like that should give us 0, 0, 3, 0. And then we can use this guy to clear that up. So we can take R3 and replace it with R3 minus 3 halves R2. And when we do that, we should get 2, 2, 0, 0, and 0, 0, 2, 0, and 0, 0, 0. And then we can have 0 there. And then we can go ahead. We want to avoid parameterizing these guys. So it looks like we'll go ahead and let x2 equal t. That first equation there gives us that 2x3 is supposed to be 0. So x3 is supposed to be 0. And then we also get that 2x1 plus 2x2 is supposed to be 0. So 2x1 plus 2t is supposed to be 0. So x1 is supposed to be negative t. So that means eigenvectors for lambda equals 1 have form minus t, t, 0. There we go. So every eigenvector for lambda equals 1 is going to be of the form negative t, t, 0. Now, in 7.2, we're going to be giving a definition here of what is called a defective or non-defective eigenvalue. And we're going to see in 7.2, when we give that definition, that the being non-defective means that the amount of free parameters or the dimension of the eigenvectors actually corresponds to the multiplicity. In this case, if we look back, right, we had lambda equals 1, but we had it show up as a root twice. However, when we actually went to get the eigenvectors for lambda equals 1, we still only found one free parameter. So we only had one free parameter, but we had multiplicity 2. That means, when we get to this terminology in 7.2, that lambda equals 1 would be an example of a defective eigenvalue. Let's go ahead and see about lambda equals 6. So we'll move on to the other eigenvalue. So now let's go ahead and find eigenvectors for lambda equals 6. So we have to subtract 6 off the diagonal and then augment with the 0 vector. So we'll have negative 3, 2, 0, 0, negative 5, 2, and then 3, 3, negative 2. Once we have that, and then augment with 0, 0, 0. All right, so we can go ahead and add this guy onto there to start with. So let's do R3 and replace it with R3 plus R1. So now we have negative 3, 2, 0, 0. Then we have 0, negative 5, 2, 0. And then when we add that on, we get 0, 5, negative 2, 0. And then we can use this guy to completely clear that out. So we can do R3 and replace it with R3 plus R2. So we should get minus 3, 2, 0, 0, 0, negative 5, 2, 0, and then 0, 0, 0, 0. So well, this time we will avoid parameterizing x1 and x2. So we will go ahead and let x3 be equal to t. Then this first equation will give us that negative 5x2 plus 2x3 is supposed to be 0. So negative 5x2 plus 2t is supposed to be 0. So it looks like x2 is supposed to be 2/5 t. Then we would also get that negative 3x1 plus 2x2 plus 0x3 is supposed to be 0. So negative 3x1 plus 4/5 t equals 0. And it looks like x1 there is supposed to be 4/15 t. So we would say eigenvectors for lambda equals 6 are of form, so they will all look like 4/15 t, 2/5 t, and t. Okay. Now, in this case, lambda equals 6 was multiplicity 1. We only had one free parameter in the eigenvector, so lambda equals 6 would be considered a non-defective eigenvalue when we talk about this in section 7.2. You'll notice that when you have multiplicity 1, you're guaranteed to be non-defective because the simple fact that you are an eigenvalue guarantees that there's going to be an infinite amount of solutions, which guarantees that there's going to be at least one free parameter. So it's only eigenvalues that have a higher multiplicity than 1 that have the potential to be defective. And that's something, again, we'll discuss in section 7.2. All right, so in this example, right, just to sort of recap why we are taking the time to do this one here, we had a 3x3 matrix, and we saw that we only had 2 distinct eigenvalues. And for each of these eigenvalues, even the one that had a multiplicity of 2 that showed up as a root twice, it only had one free parameter in terms of the description for its eigenvectors. Okay, let's go ahead and take a look at one last example. We're going to go a little bit larger than some of the other ones we've done. We're going to take a look at a 4x4 square matrix, and again do the same thing, try to find the eigenvalues and corresponding eigenvectors. So let's go ahead and do the eigenvalues. So we need to take the determinant of 1 minus lambda 0, 0, 2, 0, 1 minus lambda 0, 1, 0, 0, 1 minus lambda 3, and then 0, 0, 0, 2 minus lambda, and set it equal to 0. Luckily, this is a nice upper triangular matrix, so we can take the determinant as just the product of the diagonal elements. So 1 minus lambda, 1 minus lambda, 1 minus lambda, and 2 minus lambda, and set that equal to 0. And we should be able to very easily see that we have lambda equals 1. That's a multiplicity 3 solution, or a multiplicity 3 eigenvalue. And lambda equals 2. That's a multiplicity 1 eigenvalue. Okay, so even though this guy was a 4x4 matrix, and technically its characteristic polynomial is a 4th degree polynomial, we only found 2 distinct or 2 unique solutions, 2 unique eigenvalues. One of them is repeated 3 times, one of them is repeated just once. Let's go ahead and find the corresponding eigenvectors. So let's go ahead and start with the interesting one, where you want to do the eigenvectors for lambda equals 1. So let's go ahead and subtract 1 off the diagonal, 0, 0, 0, 2, 0, 0, 0, 1, 0, 0, 0, 3, and 0, 0, 0, 1, and then augment with 0, 0, 0, 0. Should be pretty clear, though, that we can just use this top guy to remove everything below. We can do R2 and replace it with R2 minus 1/2 R1, R3 and replace it with R3 minus 3/2 R1, and R4 and replace it with R4 minus 1/2 R1. If we do that, we will get 0, 0, 0, 2, and 0, and then everything else will zero out nicely. So for solving this, we would avoid parameterizing x4. So we will need 3 free parameters. Let's let x1 be t, x2, we usually do it the other way though, so let's go ahead and just try to be consistent. Let's let x3 be t, x2 be s, and x1 be r. Well, this top equation here just tells us that 0x1 plus 0x2 plus 0x3 plus 2x4 is supposed to be 0. So that tells us x4 is supposed to be 0. So eigenvectors for lambda equals 1 have form. Well, what would they look like? They would look like R, S, T. We have free choice of those first 3, and then x4 always has to be 0 here. So what this basically shows us is that this, in this case, is going to tell us that the eigenvectors have 3 free parameters here. When we define the concept of the eigenspace, which is the subspace that is constructed of all the possible eigenvectors for a given eigenvalue, we would see that this would be a 3-dimensional eigenspace. That matches the multiplicity, so this would be considered a non-defective eigenvalue. Notice that this also shows you guys that when you have a higher multiplicity, when your multiplicity is higher than 1, it is possible that the eigenvectors have more than 1 free parameter. All the other examples we've done so far have always had where the eigenvectors just have 1 free parameter, but that is not a restriction in general. Now we've seen a case where we have 3 free parameters. All right, we don't want to neglect the other eigenvalue though. Let's go ahead and do this also for the eigenvectors for lambda equals 2. So we'll need one more page for that. So let's go ahead and do the eigenvectors for lambda equals 2. So let's go ahead and subtract 2 off the diagonal and then augment with the 0 vector. So minus 1, 0, 0, 2, 0, minus 1, 0, 1, 0, 0, minus 1, 3, and then 0, 0, 0, 0, augmented with 0, 0, 0, 0. Interestingly enough, this is already in row echelon form. So what we would do here is we'd avoid parameterizing x1, x2, and x3, and let's go ahead and let x4 be equal to t. So then this equation right here tells us that negative x3 plus 3x4 is supposed to be 0. So negative x3 plus 3t is supposed to be 0, and x3 is supposed to be 3t. Then this equation here tells us that negative x2 plus 0x3 plus x4 is supposed to be 0. So that tells us that negative x2 plus t is supposed to be 0. So that tells us that x2 is supposed to be t. Finally, that top equation tells us that negative x1 plus 0x2 plus 0x3 plus 2x4 is supposed to be 0. And that tells us that negative x1 plus 2t is supposed to be 0. So x1 is supposed to be 2t. So that tells us for lambda equals 2, eigenvectors have form. Well, they're supposed to look like 2t, t, 3t, and t. Those would be the form there. Notice again, since this guy only had multiplicity 1, there's only ever going to be 1 free parameter for the eigenvectors there. So at this point, you guys have seen a lot of examples of calculating eigenvalues and eigenvectors. We've handled ones with all distinct eigenvalues. We've seen how to deal with complex eigenvalues, and now you guys have also seen how to deal with non-distinct eigenvalues if you have a repeated root to your polynomial equation. In our next video, we'll be moving into section 7.2, doing a slightly deeper investigation into eigenvectors and eigenvalues. We'll discuss and give a formal definition of the eigenspace, as well as what it means to be defective or non-defective.